Okay, let's look at number 4 on page 867. This is an example for section 13.1. And number 4 asks us to find the domain of a vector-valued function. The function is r of t equals the vector 2e to the negative t, inverse sine of t, and the natural log of 1 minus t. Now, as we mentioned before, in order to find the domain of a vector-valued function, we just need to find which values of t make sense for all three of the coordinates. In other words, we need to find the domain of each and see what they have in common. So let's call the first domain d sub x. So that's the domain for the function representing the x coordinate. D sub x is going to be all real numbers because this is an exponential function, and exponential functions have a domain negative infinity to infinity. Next, we're going to look at d sub y, the domain of the inverse sine of t. Now remember, the inverse sine of t has a domain equal to the range of the sine of t, which goes from negative 1 to 1. And that includes negative 1 and 1. And now let's look at the domain of z. That's a natural log function, the natural log of 1 minus t. We want to see where the argument is positive. So we solve the inequality 1 minus t is greater than 0. And that gives us that t is less than 1. So now what we want to be thinking is, what do these domains have in common? Let's go ahead and write this one as an interval as well. Notice that we're not including the 1 in this case. Now another way of saying where intervals overlap is saying where they intersect. So what we're really looking for is the intersection of negative infinity intersected with negative 1 to 1 intersected with negative infinity to 1. So what they have in common is everything from negative 1 to 1. Negative 1 is in all three sets, so that's a square bracket. 1 is not, so that's a round bracket. So this is the solution to the domain of the given vector-valued function, the interval from negative 1 to 1. Now let's look at number 6. Number 6 is basically to help us understand notation. It asks us to express a given parametric set of equations as a vector-valued function. So let's see, write as a vector-valued function, and the parametric equations that they give us are x equals t squared plus 1, y equals e to the negative 2t, so our vector valued function, we just need to give it a name. We usually give it the name r. And you can write r of t or just r. And the x-coordinate of the vector is going to be t squared plus 1, and the y-coordinate is e to the negative 2t. But they actually ask us in the book to use the ijk notation. In this case, we're in 2 space, so it would just be I and j. The coefficient of I is t squared plus 1. The coefficient of j is e to the negative 2t. And that's our vector-valued function. Now let's look at number 10. Number 10 asks us to basically reverse the procedure. So they're giving us a vector valued function and asking us to write it as a set of parametric equations. So we're going to write as parametric equations and we're given the vector valued function r equals sine squared ti plus the quantity 1 minus cosine squared t j. And so all we have to do here is identify what the x portion is and what the y portion is. X is equal to sine squared of t, the coefficient of I, and y is equal to 1 minus cosine squared t, which is the coefficient of j. And so these are the three solutions to items number 4, 6, and 10 on pages 867 to 868 of your textbook. Okay, now let's look at number 18 in section 13.1. Number 18 is on page 868. And it asks us to describe the graph of a vector-valued function's equation. That function is r equals negative 3i plus 1 minus t squared j plus tk. Okay, now there are a couple of ways to think about this as we try to describe the graph. Now, one very good clue as to what this graph is going to look like is that one of the coefficients is a constant. So if you notice, x equals negative 3 in every set of coordinates on this graph. So what does that tell us? Well, let's draw a little sketch of our 3 space here. If this is our x-axis and we come out, actually we want to go back to negative 3, so we're going back 3 units on our x-axis. Let's say that's negative 3. Right, then that means that every point on our graph is going to be 3 units behind this YZ plane. So everything on our graph is going to be in this plane that cuts through the point negative 3, 0, 0. Okay, so that's back behind the axes. Alright, so no matter what else we know about the points on our graph, they have to be in that plane. Or another way of saying that is whatever shape is formed by 1 minus t squared and t, it's going to intersect that plane, and that's where our shape will be traced out. Alright, so let's talk about what the 1 minus t squared and the t are going to do. Well, looking at this now, forgetting about the x coordinate, what if we were just going to graph a function that had the variables y and z? In other words, we're looking at the yz plane. Well, in this case, our y coordinate is always going to be 1 minus t squared, and our z coordinate is always going to be t. Or another way of thinking of that is if z is equal to t all the time, then y is equal to 1 minus z squared. So in our yz plane, we're going to have a parabola, and y is a function of z, so it's going to be a sideways opening parabola, and it's going to open towards the negative side because the z squared term is negative. So let's just sketch that in there real quick. Okay, so for example, if z was equal to 0, y would be equal to 1. So we have the point here, which in z space, or sorry, in the yz plane, would just be the point 1, 0. But if we throw the x value in there, we're going to be actually 3 units back, and so this is going to be the point 1, 0, or actually, sorry, x comes first. This is going to be negative 3, 1, 0. It mirrors this point up front here, but it's taking place in the plane that goes through 3, 0, 0. Okay, now if we were just in the yz plane and we had y equals 1 minus z squared, then for example, if y was equal to 0, then we would have 0 equals 1 minus z squared, which would mean that z would be plus or minus 1. So those points would be located at 0, 1 and 0, negative 1 in the yz plane, but throwing that third dimension in there, the x coordinates, we're going to be up 1 from the x-axis here and down 1 from the x-axis here. And so what we see is the start of this parabola So this is going to be a parabola inside the plane where x is equal to negative 3. Now they didn't actually ask us to draw it, which is a good thing because this drawing I know is a little bit rough here. What they asked us to do is to describe it. So to write this down, what we're saying is that the vector valued function r equals negative 3I plus 1 minus t squared j plus tk traces out a parabola in the plane x equals negative 3 through the points negative 3, 0, 1, negative 3, 0, negative 1, and negative 3, 1, 0. And that would be an adequate way of describing this vector valued function. let's take a look at number 34 in the same section on page 868. Okay, number 34 is similar in that they're going to give us a vector valued function and ask about the graph. But in this case, they want us to sketch the graph, and they also want us to include, and you really have to be accurate, the direction of increasing t, in other words, the orientation. So we're going to have to put in the little arrows. So the function that they're giving us to graph is r equals ti plus tj plus sine of t times k. And again, they're asking us to graph, and really they shouldn't have to tell us to include the orientation. When they say graph a vector valued function, it's assumed that the orientation would be included in that graph. Okay, so as a solution, we have a little bit of analysis to do here. We need to try to figure out some characteristics that are significant about the coefficients here. And it might help you to kind of get an idea of what's going on if you write out the parametric equations that represent it. X equals t, y equals t, and z equals sine of t. Okay, so one thing that I noticed that's significant here is that both x and y are equal to t, which tells me that x is always equal to y. Now in 3 space, what does that tell us if we know that x is always equal to y? So let's draw a little graph here and see if we can visualize this. Here's my x, here's my y, and here's my z. Okay, now what if we weren't in 3 space? What if we were just looking at the xy plane? So we're just going to come down here and just look at the xy plane. Well, in the xy plane, the line x equals y cuts right through on a 45-degree angle through the first and fourth quadrants. So this would be the line where x is equal to y. But this is 3 space. And so not only does this line satisfy the equation x equals y, in fact, these would be all of the points x, x0, or t0, depending on how you want to think about it. But also, if we move up a notch on the z-axis, we would have another line here, right above. Okay, and this line would also satisfy the condition that the first and second coordinates were the same, and then the third coordinate might be 1 or 2, depending on our scale here. So let's say this is TT2, and so on. And so what we have is a plane that goes through the z-axis and through the line x equals y in the xy plane. And what we know is that no matter what the restriction of z, we have to stay within this plane. Okay, so now let's consider what this z equals sine of t is telling us. Well, for one thing, z equals sine of t, well, we know that the t here is equal to both the x and the y. So we can either think of this as being equal to the sine of x or the sine of y, whichever we feel is more convenient. I'm going to choose to think of it as sine of y, and the reason is because I find it easier to graph in the yz plane because it's facing forward. So I'm going to change the color of my pen here, and I'm going to try to sketch what z equals sine of y would have looked like. Now, the y-axis is our domain of our function. So, and by the way, I forgot to include this function, as I have it written, would have a domain of all real numbers, but in the book they've asked us to restrict our t values to being between 0 and 2 pi. Okay, otherwise it would just repeat forever, which is okay, but we're just going to graph one period. Alright, so let's say that this is pi over 2, and this is pi, and this is 3 pi over 2, and this is 2 pi on the y-axis. Then we would have pi over 2, pi, 3 pi over 2, and 2 pi on the x-axis as well. And the reason why I want to mark those off is because we know that, again, we're looking to have all of the values going along the line x equals y here. So we want to keep in mind that these need to line up. Now, if I were to just graph in the YZ plane, I will not be graphing in actual values that are on our final graph. I'll just be getting an idea of basically kind of like a shadow of what my graph would look like if I looked through the plane where we know it appears. So what I'm saying is that if we completely ignored the condition that x has to be equal to y, we could just graph our regular old sine curve. I guess if this is t equals 2, I better make it a little shorter here. Okay, so our sine curve is going to go up to 1, down to 0, down to negative 1, and back up to 2 pi. Okay, but those points are in the YZ plane, and my graph will not be in the YZ plane. What my graph is going to be is, if you can imagine sliding this sine curve forward along the x-axis and seeing where it intersects this diagonal plane that's coming out towards us where x equals y. And so what's going to happen is, instead of going through the point 0, 0, we're in 3 space now, so we're going to go through 0, 0, 0. Okay, so here we have 0, 0, 0. Alright, instead of going through the point pi over 2 for y and 1 for z, we also have to take into consideration that x is also equal to pi over 2. So we're going to come out to pi over 2, pi over 2, and up 1. Maybe about here. Okay, and that was where the peak of the sine curve moved to, and that would be the point pi over 2, pi over 2. You know what, I can't write that small. Hold on a second. Let's see. Okay, so the peak of the sine curve is going to be at pi over 2, pi over 2, 1. Okay, then after the peak we come down to 0 at pi. Now that means that we're going to be at pi pi, which would be here, but we're up to 0. Well, actually, no, we're still at 0 here, so we're going to go, we have our peak of our sine curve, we come back down to 0, again along this line x equals y in the xy plane. Then we're going to actually dip below the plane. That's this dip right here. So this would be at 3 pi over 2, 3 pi over 2, which is along this xy, x equals y plane, but then we're going down 1. So the valley of this graph is going to go down like this. And then at 2 pi, 0, we're back up to the xy plane. So this sine curve is coming towards us at an angle. Now we need to put in our direction. So when t is equal to 0, what is r going to be? Well, r of 0 we already said was 0, 0, 0. So this is the initial point, the starting point for our vectored value function. And we're going to move along until we get over to 2 pi. So I need to put in some arrows indicating that. We're starting at the origin and moving out away from the origin towards the front of the graph. And that's the solution to number 34.